These are the first part of the notes for Friday, and we're actually 6.2. Sorry, got a typo there. We are going to be working with slope fields. And so we've been working with differential equations. And remember, a differential equation is one where you're given the rate of change as either a function of y, of x, both x and y, and we've been separating. So we've had ones like this where we can separate, integrate, and if we're looking for a particular solution, we've been able to find our constant of integration. And we've been doing that with what we call analytic methods. And analytic methods basically just means with algebra. But it's not always the case that every differential equation is separable. It doesn't mean it can't be solved, but a lot of them can be solved with higher levels of calculus. There's a whole class called differential equations where you learn how to solve all kinds, but there's even some where it's not even possible to solve it. That doesn't mean, though, that we can't still get a good idea of what the original function was or what the solutions are. And there's a graphical way, and that's called graphing a slope field. So what a slope field is it's a graphical representation to the general solution. Now, that just seems like a lot of words, so let me off to the side here go like this. Suppose dy dx equaled x plus 1. We know that we could solve that one. We could just multiply the dx over and integrate, and I'm going to get a second degree or a quadratic equation, which makes sense because the derivatives knock powers down. So if my first derivative is x to the first, my original function must have been a quadratic. What this means, though, for the slope field is that when I make it, I am going to see a bunch of parabolas that differ via vertical shift. So if I were to go graph that at x equals -1, I will see horizontal little tangent lines. Going to go like that, and then what's going to happen is they're going to go like this, and you might say, what is she doing? This you'll get in a little bit because we're going to go make some. But oops. But when you squint and go with the flow for this one, you see a family of parabolas forming when you kind of squint and follow those tangent lines like wind flow. And this right here is called a slope field, and it's a graphical solution or visual to the differential equation. So that's just some vocabulary. Let's just hop in right here and go do one. So this says to draw a slope field for the differential equation where the derivative is equal to the x squared. Well, let's just hop on and do this. Let's hop on, and again, we're going to do this at these corner points. So I'm going to hop on, and you might say, oh my gosh, that's so many. Not when you actually get going, because the derivative everywhere is the x-coordinate squared. So right here at -2, 2, the derivative is going to be 4, which means I'm going to right now make a very steep uphill little tan line. I'm going to make it big enough so I can see it, but not so big as to interfere with my other tangent lines. But it's not dependent upon x. It's only a function of of y. It's only determined by its x coordinate. So everywhere along the line x equals -2, I'm going to have these very steep tangent lines that have a slope of 4. Likewise, on this line where x is -1, it doesn't matter what y is. The derivative is going to be -1 squared, or 1. So I'm going to make little tangent lines that have a slope of 1. Everywhere where x is 0, my tangent line will have a slope of 0 squared, or 0. Everywhere x is 1, I'm going to have slopes that are the same as on that side. And I am creating a slope field. I'm creating a graphical representation of the solutions to this differential equation. Now I could have gone out forever and I could have made my tick marks smaller and gone by halves and had more tangent lines in here and filled in the grid, but suppose I were to go through 1, 1 and draw the particular or specific solution. Again, when I do the general slope field, I get a visual of all solutions to the differential equation, and they all differ by some constant, and on this one that constant causes vertical shifts. But if I were to kind of drop in a feather right here and the wind were to pull it this way, and then it's going to kind of go like, and notice I don't have to go through the marks, only the one that I'm finding the solution for. If you look at this red solution to the general differential equation, it looks like the graph of a cubic, and that shouldn't be the least bit surprising because this one is separable or solvable with analytic methods. I can just move the dx over. I can integrate. The antiderivative of 1 with respect to y is y. The antiderivative of x squared is x cubed over 3. And here's that constant of integration that's causing the vertical shifts to happen. So that's why if I were to say draw the solution through this one, we'd kind of go like that and like that. Oops, not the best one, but I'd get another one. It'd just differ by a constant. So my analytic methods and my slope field visual are both yielding a cubic general solution. So let's go to the next page. So on this next page, this isn't in your notes, but I kind of screenshot a really funky slope field, but the original would not have been a function because you can see it doesn't pass the vertical line test, but it's kind of cool. And if you can't see this one, this is a weather map that's charting wind flows, and sometimes slope fields are called vector fields, and so I don't know if you can see this very well. It didn't screenshot in very well, but it's got these little arrows at the end of it because it's actually a slope field and a vector field is kind of the same way, but this is showing wind current. So if I were to drop in a feather right here, how would the wind take it? And it looks like it's going that way. And then I think it's hard to see on here. But again, it's similar to the effect of what a slope field does. It takes you along different tangent lines as you travel through the field. So it says on the top, a couple things to keep in mind. When you're drawing those little tangent lines, make sure you make them big enough so you can see them and follow them if you need to, but make sure they don't interfere with your other tangent lines. Note numero dos. Make sure your slopes of 0, 1, and -1 and infinity are spot on. 0, anywhere the slope is 0, make sure you have a completely horizontal little tan line. Anywhere it's 1, make sure it looks like a 45-degree uphill angle. -1, likewise. And when our slopes are infinity, we have vertical tangent lines. So I'm going to have you draw an arrow over here. A slope that goes to infinity is basically where a horizontal asymptote occurs. And remember, that's when you get some number over 0. So what that means is if you had y equaled 5 over x minus 2 and you were trying to draw the dy dx differential equation and you were trying to draw the slope field for that, everywhere x is 2, I would have 5 over 0, and what that means is everywhere x is 2, I'd have vertical tangent lines, and so I'd go like that and I'd create an asymptote on my slope field. But if you get 0 over 0, that truly does not exist, and what that means is you don't draw any tangent line. So there's a difference here between an infinite slope and a slope that does not exist. All right, so this is the last one that we just did. This was the y equals x squared. It's just we've got Mathematica kind of expanding that out so you can see it better. And now if you squint, you can really go with the flow on that one. It's the same one that we just did a snippet of on the previous page. So we're going to hop in here. And it says, as previously mentioned, sometimes we don't know the formula or the solution to a differential equation. In cases like that, the slope field's a really good way to get the visual for what the general particular solutions look like. Let's go try it. So this one is y prime dy dx, the differential equation, is equal to the x plus the y's. Now, don't put this in your notes, but just for fun, let's suppose you tried to separate this. Dy dx is equal to x plus y. How could I try to separate it? Legal to multiply both sides by dx? Sure. Now I've got a set of parentheses being multiplied by the differential, or dx, so I guess that would yield x dx plus y dx. Okay, what am I trying to solve for? I'm trying to solve for y, Mrs. LaRude. Okay, well then let's get everything else out of the way. Let's do dy minus x dx is equal to y dx. And again, I'm attempting to try to solve this analytically. Now I'm just going to divide everything through by dx, and I'll get dy dx minus x is equal to y. Oh boy, now I've got dy dx is equal to y plus x. What? Here we go loop-de-loo, right? I went right back to where I started. So my analytic approach did not work for that, but it's only because the only analytic approach I know right now is separation of variables. There's a higher levels of math beyond the scope of this course where you actually will learn how to solve that linear differential equation. But for us, we can only get a visual of it because that's all we know how to do. And we're going to go do that. Everywhere along these little tick marks that have been given, only do it where indicated, we are going to add the x plus the y. We're going to get our dy dx, or our slope, and we are going to go make little dashes that follow that slope. So let's begin. Up at negative 2, 1 in this top corner, I would do negative 2 plus 1 is negative 1. So I'm going to have a slope of negative 1. So downhill at about a 45-degree angle. Whew, that was so hard. Wasn't that difficult? Not at all. All right, so sometimes it's nice to kind of figure out where will the slope be 0, because that's kind of good. So let's hop in here. Maybe I could get a whole bunch for one little manipulation. Dy dx is going to equal 0 when y is the opposite of x, or when they're opposites, like here at negative 1, 1. 0, 0, 1, negative 1, and I just got 3 for 1 knowing that. Let's just hop on right here at negative 2, 0. I do negative 2 plus y, which is negative 2. At negative 2, negative 1, I'd add them and get a negative 3. So I just need to make that steeper than I made the negative 2 one. At negative 1, 0, I'd get a negative 1. At negative 1, I'd get negative 2. At 0, 1, I'd get 1 for my slope. And again, I'm just adding the x and the y to get me the slope of the tangent lines on that area of the grid. At 0, negative 1, I'd get negative 1 again. At 1, 1, I'd get 2, and then 1. And let's see, at 2, 1, I'd be 3, very steep, and then 2, and then 2 plus, and then 1. And I've got this really kind of wonky looking snippet of the x plus y graph. And let's go see that. And again, this is just giving me a little bit of a screenshot. If I squint and have my feather follow those wind flows, what will the solution that goes through 0, 1 look like? So I go to 0, 1 and I put a dot here. That I must go through. And then I go with the flow. If that feather falls right there and gets taken to the right, it looks like it's just going to kind of go right up off the screen. So go ahead and draw that. If it goes to the left, watch what's going to happen. Everywhere y is the opposite of x, I'm getting horizontal tangent lines. That means that would happen at negative a half, and negative a third. I only did it at those nice integer values, but everywhere along here, I actually would have horizontal tangent lines. So when this feather approaches these, it's going to take and curve back up, and it's going to go right along this, and that's going to kind of create a slant asymptote. So that's what my graph is going to look like over there. How about at negative 1, 0? Let's go look at that one. How's the wind going to take the feather if it lands right above negative 1, 0 and I go with the current? If I go to the right, the wind is going to consistently go that way and take it. And if I go to the left, it's going to go like that, and I get a line. Kind of interesting because you'll see that the solutions to this one aren't the same. They're not symmetrical. They're not just varying by some vertical or horizontal shift. So kind of neat that I'm getting different solutions. Now there's a program. Actually, there's lots of computer programs, including one that's out there for the calculators, but that one's not very good, that does these. So I'm going to go take a minute, and I linked this to your Schoology. I'm going to go to GeoGebra and show you a little slope field plotting here. So it's going to put, the reason I chose this one is it's its default. So up here pops x plus y. And I've got this little snippet from, they're going from -5 to 5. We just went from -2 to 2, I think. We just did this portion right in here, right? And I can shrink that down by messing with the density, so you can kind of pull on that. But you can take a point, and we did our solution field through -1, 0. Look at, there's that vertical line I drew. We also did it through 0, 1, and we're getting that same curve. It's just our slope field didn't have nearly as many tick marks, and you can make them more dense. I'm gonna mess with this for a second. See, I can really get a good visual. As you make that more and more dense, you can really get a good go with the flow. If I go out more, oops, sorry. Oh, now I'm getting the spinning wheel of doom, but you get the idea. Hopefully, I might need to stop the recording here and redo another one of that. Oh, okay, I'm good to go. So you can pull, I wonder if it'll let me pull it. You know, it's not liking me right now. So a good enough idea, and I've linked that to your Schoology folder. So if you want to check your homework, you can go enter in this box right here your differential equation, and you can go mess with the density right here, and you can pull on the points to change the solution, and you can kind of see what that looks like. I'm going to get out of that right now, though. And I'm going to continue with notes till it hits 20 minutes, and then I'll make another video. So moving on to the next page, my page turner. All right. So let's go. I'm going to get my window in here a little better. And let's see if I can. I'm trying to move my screen capture box. Oh, there we go, box. So you can see